Hi, I'm Bashima. I'm an assistant professor in the Department of Electrical and Computer Engineering at Worcester Polytechnic Institute. Today, I want to talk a little bit about sustainable intelligent everyday objects. Computing is getting integrated into our everyday life, and the objects we use are getting smarter. I envision that the future of sustainable computing will reshape how everyday objects will behave and influence human life by continuously learning human behavior, our actions, and the environment around us. These everyday objects will contribute to the welfare of human, planetary, and infrastructure health. These intelligent objects falls into the realm of Internet of Things or IoT. And with ARM's prediction of having 1 trillion IoT devices by 2035, the rising question is, how are we going to power them? One of the obvious answers is we will use batteries, right? But think about it. With 1 trillion IoT devices, how many batteries we need to recharge or replace? And recharging and replacing so many batteries will be inconvenient and costly. But what is the number actually? Now, let's say that even if the battery technology is reaching its goal and develop batteries that can last for 10 years without any recharging, we will still end up replacing 274 million batteries every day, which is equivalent to 9 Empire State Buildings every year. Now, let's say even if we decide to go through this maintenance hassle, it is still hazardous to the environment and is ecologically unsustainable. Now, battery being one of the biggest bottlenecks in the growth of IoT industry, we want to move from batteries towards more sustainable energy sources like solar, kinetic, and radio frequency. Let's just imagine that what if you can power your IoT devices not only using the sun, but also from the power you generated when you're running or even from the Wi-Fi you are using. Now, these batteryless devices are a perfect candidate for realizing the vision of sustainable computing dust that will sense, compute, and learn forever. They will be applicable in various application domains, including health monitoring, biodiversity preservation, and catastrophe prediction. Now, let us take a look at why or how these batteryless devices are different from traditional Internet of Things. Traditional Internet of Things primarily uses sensors to collect data and send it to the cloud for computation. Recently, to reduce delay and to ensure privacy, another computing device connected to the local network has been added to the picture. These devices perform early data processing and are called the edge. However, it is still not sufficient due to the limited bandwidth and the high communication energy requirement. To address this, we need to move computing from the edge devices to the IoT devices themselves. Now, the low processing capability, small memory footprint, and limited energy of these IoT devices introduce extreme constraints, and thus I call them extreme edge devices. However, these batteryless extreme edge devices comes with own challenges. First, most ambiently available energy is insufficient to power this device directly. So we need to accumulate enough energy before we can even use it. Next, the low power microcontrollers used in these devices have limited processing capability and limited memory that often results in longer processing time. Besides, the harvestable energy often depends on the stochastic environment, which we have no control over. So we need to design systems that can provide the best outcome and evolve with the environment despite these constraints. My vision is to develop a new set of sustainable extreme edge computers that are reliable, intelligent, self-evolving, programmable, and user-friendly. Now, let us take a look at an example describing why these characteristics are needed. The example scenario is based on one of IBM's existing project, Project Rhino, which aims to stop endangered rhino poaching. IBM monitors a herd of impalas who share the same food habit as the rhinos to predict approaching poachers and inform the forest rangers who will stop the poaching. It is a perfect case for a batteryless system, and it is hard to charge or replace batteries in sensors attached to the herd of impalas. Now, such a system must be reliable because the forest ranger needs to be informed before the poacher can reach the rhino. Thus, the processing needs to be finished within a deadline, and it needs to be secure so the poacher cannot change the incoming text message. Otherwise, the ranger will not be able to stop the poaching. Next, the system needs to be intelligent enough to differentiate between a poacher and a lion. If it is often wrong, the forest ranger will not trust or even use such a system. Next, it needs to be self-evolving over time with the migration of the impalas and the change in their behavior. Such a system needs to be programmable, so we do not need special developers and can easily produce and update such a system. Finally, it needs to be user-friendly for both the impalas and the forest ranger, and that can happen when it fulfills application-specific requirements. Now, my research focuses on three larger areas for sustainable lifelong sensing and computing. The first one is on-device artificial intelligence and learning. I worked on shifting the capabilities of tiny computers from sensing to decision-making. And to do this, the goal of this project is to design optimal deep neural network models for battery-powered and battery-less resource-constrained systems. Now, these devices will be deployed in hard-to-reach scenarios and will be active for a long time. Thus, they will experience a lot of unlabeled data, as we are not storing or sending any raw data, and a vast amount of data will be wasted if we do not adapt or learn from them. Therefore, the next project explores semi-supervised, unsupervised, active, and federated learning and develop low-overhead model adaptation techniques for lifelong learning. The next bigger domain of my research focuses on secure real-time platform. I have 3 running projects. The first one is in collaboration with the Computer Science Department of WPI, which works on formal verification of batteryless system. The secondary project is a part of a bigger team with Northwestern University, University of Theodulf, and University of Trento. It also involves Maxim, which is recently acquired by Analog Devices. And here we are working towards developing a generalized batteryless platform and runtime for deep neural network in batteryless devices. The final larger domain focuses on application domains and how we can adapt to them. In collaboration with University of Illinois at Urbana-Champaign, I'm working on child development monitoring using on-body sensors to understand their mental development, low-power localization, and hearable computing. Another project is going on with a collaboration with Carnegie Mellon University for equipping wheelchairs with sensing capabilities. And the final one is a dear project to me, which is hybrid computing and opportunistic networking in intermittent system or batteryless systems. So these are a part of the projects we're currently doing in Bash Lab. And if you find any of this project interesting, want to work with us or collaborate with us, please look at our website, look at what we are doing now, and feel free to send an email, and we'll be happy to work with you and collaborate with you. And we are also looking for students to join the lab. So if you're interested, please apply. Thank you for listening to me.